Hey guys, in this video we're going to talk about VSEPR theory and how it allows us to predict the shape of molecules. So how does this work? Well, first of all, what does VSEPR theory mean? Well, it's VSEPR, valence shell electron pair repulsion. So what does that sound like? Well, it sounds like we've got electron pairs in the valence shell that are repelling each other, and that's exactly what it means. So I'm going to show you an example here. Let's say you have a central atom A, and it's got atoms attached to it, all the same X. And let's say it looks like this. So what are these bonds made of? Well, they're made of shared electrons, right? And they all form electron clouds, which are all negatively charged. And we know that negative charges repel each other, so they're going to want to be as far apart as physically possible. So what's actually going to happen here are that these side bonds are going to become shifted up slightly. And it'll look like this. So think about why this would have happened. Well, now the distance between all of these electron clouds has been completely maximized. Now the molecule is happy. It has completely maximized the distance between its negative charged electron clouds. So notice how just by knowing how these electrons are placed around a central atom, we can predict the molecule's overall shape. It's going to be shaped like a kind of like a triangle. See that? So that's what this big scary chart summarizes. This chart essentially tells you, based on how the electrons are placed around a central atom, what the molecule's shape is going to be. So we're going to run through an example of every molecular shape that you're expected to know. And in order to do this, I'm going to give us a bunch of example molecules for which we will have to draw the Lewis dot structures. So you'll see that drawing Lewis dot structures is absolutely vital for utilizing this chart. So I want to start with the molecule here. Beryllium fluoride. So the first step is we draw its Lewis dot structure. So the first step is we pick a central atom. And this is going to be the atom that we only have one of, or that we have the least of. So it'll go in the center. Then I'll draw my skeleton structure, so I'll attach the fluorines to the beryllium. And then step 3, I distribute my valence electrons. So in order to do that, I need to figure out how many valence electrons I have total to work with. So to figure out how many valence electrons I have, I go to the periodic table and I look at all of these elements' group numbers. So beryllium, this is in group 2A, so it's going to contribute 2 valence electrons, while fluorine is in group 7, so it'll contribute 7 valence electrons, but there are 2 of them, so 7 and 7. So 2 plus 7 plus 7, we have 16 valence electrons to work with total. So we've already used a few electrons to make these bonds, right? There's 2 electrons in this bond, so 2 here, 2 here. So we've used 4 already. So now we have 12 left. Well, now we have to satisfy the octet rule. So I'll start placing my extra 12 electrons on these outer fluorines. So now this fluorine has 1, 2, 3, 4, 5, 6, and then 7, 8, 2 from this bond. So it has 8 electrons. It's happy. It's satisfied its octet rule. That's what the octet rule means, that you have 8 electrons in your valence, and that's what most atoms want. So I'll do the same over here, using the rest of my electrons. So now I have 1, 2, 3, 4, 5, 6, 7, 8 electrons on this fluorine. Well, have I used all my electrons now? So I used 2 for this bond, 2 for this bond, so there's 4. So 4, 6, 8, 10, 12, 14, 16. Yep, I used all 16. So everything better be happy. And by that I mean everything better have a satisfied octet. Well, I already checked that both the fluorines have a satisfied octet, but the beryllium only has 1, 2, 3, 4 electrons in its valence. And usually things want 8, right? But it turns out beryllium is psyllium because it only wants 4 electrons in its outer shell. So this is actually a satisfied octet because it's an exception to the rule. So this means our Lewis dot structure is complete. So now all we have to do is find this information in this chart up here. So the first thing I do is I figure out how many regions of total electron density do I have. Well, what is a region of electron density? An example of a region of electron density would be this, 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 or this. These are all examples of regions of electron density. This is one region of electron density, one region of electron density, one region of electron density, and one region of electron density. So in this molecule, we have 2 regions of electron density. So let's find that in this row. I'm sorry, in this column. So the only option we have with 2 regions of electron density is this first row. So that means our electron geometry is linear, our molecular geometry, and note, molecular geometry is the actual shape of the molecule, okay? So this means that this molecule is going to have a linear shape. And I've got a picture of that right here. So it's going to look exactly like this. So that means the beryllium is the red circle and the fluorines are the green circles, and it's a perfectly straight line, just as linear the name suggests. So notice how the rest of the row matches up. There are 2 bonded regions. And remember, this chart is all in reference to the central atom. There are 2 bonded regions to beryllium, 0 lone pair regions on the beryllium. The bond angles here, this is actually going to be 180 degrees. And the hybridization on the beryllium is sp. So let's move on to another example. Okay, what about CO2? So step number 1 for the Lewis dot structures, I set my central atom. So there's only 1 carbon, so that'll be my central atom. I'll attach my outer atoms to draw my skeleton structure. And then I distribute valence electrons, so I have to figure out how much I have to work with. So carbon, I have 4 because it's in group 4A. Oxygen, it's in group 6A, so I have 6 and 6 because there are 2 of them. So 4 plus 6, that's 16 total to work with. And again, I've already used 2 here, so 2 bonds, so 4 total. 2 electrons for this bond, 2 electrons for this bond, so I've used 4 total. That means I have 12 left. So let's start placing the electrons to satisfy the outer atoms octets. 1, 2, 3, 4, 5, 6. Okay, so now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So both of the oxygens have satisfied octets, and I've used all my electrons, right? Because I've used 6 here, and then 2 here, and 2 here. So 6 plus 6 is 12, plus 2 is 14, plus 2 more is 16. So the problem is, though, I don't have a satisfied octet for my carbon. Carbon wants 8 electrons, right? So what I have to do here is adjust the lone pairs or the bonds to satisfy the octet rule. And also I have written up here formal charge, you have to adjust for that in certain cases. So that's less common. You really always want to look at the octet rule. The formal charge is really only more important when you're looking at something like a resonance structure. So how do we satisfy the octet rule for the carbon? Well, it needs more electrons, right? So what we can do is take some lone pairs from the oxygens and turn them into bonds. So I'll make both of these double bonds. So now the carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its valence shell, and it has a satisfied octet. Notice how both of the oxygens still have satisfied octets. So 1, 2, 3, 4, 5, 6, 7, 8. So this is our completed Lewis dot structure. So now let's find the information on the chart. So I have 2 regions of electron density. And again, only the first row has the option of 2 total regions of electron density. So again, this molecule is going to be linear with a bond angle of 180 degrees, and the carbon is going to be sp hybridized. So let's move on. Okay, so the next one I want to do is BH3. So BH3, I'll pick my central atom, so that'll be the boron, and then I'll draw my skeleton structure, so I'll attach my outer atoms. And then I'm going to distribute my valence electrons, so let's see how many I have total. So boron, you go to your periodic table and you see that boron is in group 3A, so it contributes 3 valence electrons. Hydrogen, each of those contributes only 1 valence electron. So 1, 1, and 1, so 3 plus 3. So we have 6 total valence electrons to work with. But if you notice here, we've already used 2, 4, 6 valence electrons. So we actually don't have any more electrons to place. So this better be a completed Lewis structure with everything's octet satisfied. So let's check and see if we have to adjust. So each hydrogen is an exception to the octet rule in that it only wants 2 electrons in its valence shell. So 1, 2, 1, 2, 1, 2. They're all satisfied. Boron is a moron because he only wants 6 electrons in his valence shell, but that's what he has, right? 1, 2, 3, 4, 5, 6. So everything is happy. This is our completed Lewis dot structure. So let's go up and see if we can find this information in the chart. We have 1, 2, 3 regions of electron density total. So there are 2 options for this molecule, but see how they differ here? One of them says all 3 are bonded regions. The other one says only 2 of them are bonded regions. But we know here that all 3 of these are going to be bonded regions because they're all bonds. So this is going to be a trigonal planar electron geometry, and its shape or its molecular geometry is going to be trigonal planar, and the angles between each bond are all going to be 120 degrees. And the hybridization on the central atom is going to be sp2. So I've got a picture of this shape right here. So I hope that one makes sense. Okay, so the next molecule I want to do is SO2. So I'll pick my central atom, that's sulfur because there's only 1, and then I'll attach my outer atoms to draw my skeleton structure. Then I'll distribute my valence electrons, so I've got 6 electrons from the sulfur because it's in group 6A, and oxygen is also in group 6A, so it'll contribute 6 electrons each. So 6 plus 6 plus 6, I have 18 total electrons to work with. I've already used 4 for these bonds, right? So that means I have 14 left. So I'll start satisfying the valences of these outer oxygens using up some of my electrons. So now both of these oxygens have satisfied octets, right? 1, 2, 3, 4, 5, 6, 7, 8, same over here. So I just used 6 and 6, 12 electrons for the lone pairs, and then 4 more from the bonds. So that means I've used 16. So I have 2 more electrons to use, right? Well, the only place I can put them is on the central atom. So I'll go ahead and put them here. And now I've used all 18 of my electrons. So we know the oxygens have satisfied octets, but what about the sulfur? Well, it's got 1, 2, 3, 4, 5, 6 electrons. And it's not an exception, it wants 8. We don't find it under the exception rules. So how can we give sulfur more electrons? Well, we can steal an electron pair from one of these oxygens and turn it into a double bond. So now the sulfur has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its valence. And it's satisfied its octet. Notice how we didn't mess with this oxygen's octet either. 1, 2, 3, 4, 5, 6, 7, 8. So everything's happy. So now we have 1, 2, 3 regions of electron density. One of them is, 2 of them are bonded regions and 1 of them is a lone pair region. So 3 regions of electron density total. It's one of these. So 2 of them are bonded regions and 1 of them is a lone pair region. So it looks like we're in this row. So that means the electron geometry is trigonal planar and the molecular geometry, or SO2's actual shape, is bent. The angles between these bonds are less than 120 degrees and the hybridization on sulfur is sp2. So let's look at what happened here. So the electron geometry was trigonal planar, so I like to think that that's how we kind of started out. And then by taking away this bond here and turning it into a lone pair, imagine you chopped off one of these bonds and turned it into a lone pair. Now that lone pair is going to be pushing down on those bonds, shortening the angle between the two bonds, making it less than 120 degrees. So this is its actual shape. This is its molecular geometry. So I hope that made sense. Okay, continuing on here, the next molecule I want to draw is CH4. So my central atom here is going to be carbon because there's one carbon, and then I'll attach my outer atoms. And then, so I drew my skeleton structure. So now I need to distribute my valence electrons. So carbon has 4 because it's in group 4A. Each hydrogen has 1. So it has 4 total. So 4 plus 4, we have 8 total. But we've already used 8, right? 2, 4, 6, 8. So everything must have a satisfied octet. We know hydrogen is an exception because it has only a requirement of 2 electrons in its outer shell, and they all have that, 2, 2, 2, and 2. Carbon has 8, right? 2, 4, 6, and 8. So everything is happy. So we have 4 regions of electron density, all bonded regions. So let's find this in the chart. So 4 regions of electron density, all of them are bonded regions. So the electron geometry is tetrahedral, and its shape, or its molecular geometry, is also tetrahedral. So notice how these are sometimes the same, but there are other examples where they're not, and we'll get to that. So that means the angles between the bonds are 109.5 degrees, and the hybridization on the carbon is sp3. So I drew a shape of this on the board, but it's not really accurate in 3 dimensions. So this is really what this is going to look like, where the carbon is the red atom, the hydrogens are the green atoms, and you can see that this maximizes the distance in 3 dimensions from each bond. So hopefully that makes sense. Let's move on to another one. Okay, so let's do NF3. So I'll draw my central atom here, nitrogen, because there's one of them. Draw my skeleton structure by attaching the outer atoms. And then distribute my valence electrons. So nitrogen is in group 5. Fluorine is in group 7. So 5 plus 21. I have 26 electrons here to work with. So that means I've already used 2, 4, and 6, I have 20 left. So let's start satisfying the octets of these fluorines. So now they all have satisfied octets. They have 1, 2, 3, 4, 5, 6, 7, 8, each of them. But how many electrons have we used? How many do we have left? Let's do a count. So we use 6 here, 6 here, and 6 here for the lone pairs. So that's 18, and then 20, 22, 24. So we have 2 left to use, right? So the only other place that we could put these is actually on the central atom. So let's make sure everything has a satisfied octet. We already checked the fluorine, so what about the nitrogen? Well, it wants 8 because of the octet rule, so 2, 4, 6, 7, 8. So we're good, everything's happy. So we have 1, 2, 3, 4 regions of electron density. 3 of them are bonded regions, and 1 of them is a lone pair. So let's find this on the chart. We have 4 regions of electron density, so it's one of these 3. But we have 3 bonded regions, so this row, and 1 lone pair region. So the electron geometry is still tetrahedral this time, but now the shape is trigonal pyramidal, and the bond angles are now less than 109.5 degrees, but the hybridization is still sp3. So let me show you a shape of what this actually looks like. So the nitrogen is the red circle, and the fluorines are the green circles. So you can see here that in contrast to our last shape, you replaced that top bond with a lone pair, right? So now you can see that this lone pair is going to be pressing down on those 3 bonds making the angles between them less than 109.5. So when you swap out a bond for a lone pair, you change the shape of the molecule from tetrahedral to trigonal pyramidal. So let's draw the next molecule here, water. So I'll pick my central atom. There's only one oxygen, so that's the center. And then I'll attach my outer atoms to draw my skeleton structure. Then I'll distribute my valence electrons. So I have one valence electron from each of the hydrogens because they're in group 1A. And then I have 6 valence electrons from the oxygen because it's in group 6A. So 6 plus 2, I have 8 total to work with, right? So I've already used 4, 2 for this bond and 2 for this bond. So I have 4 left to use. Well, the hydrogens already have a satisfied octet, right? They only want 2, and that's what they have. 1, 2, and 1, 2. So I have 4 left, and the only place to put them is on the oxygen. And that actually perfectly satisfies the oxygen's octet now. Now it has 1, 2, 3, 4, 5, 6, 7, 8 electrons, which it wants. So everything's happy. So we have 1, 2, 3, 4 regions of electron density, 2 are bonded regions, and 2 are lone pair regions. So where is that on our chart? Well, it looks like this row, right? 4 total regions of electron density, 2 are bonds, and 2 are lone pairs. So the electron geometry was tetrahedral. The molecular geometry, or its actual shape, is bent, and the angle is even less now. It's less than it was before for the last molecule. Now it's even less than that, so much less than 109.5. And the hybridization on the oxygen is now sp3 still. So we kind of started out with this electron geometry, and then we replaced 2 of these bonds with lone pairs. So now it looks like this, right? This is what water looks like. It's got a bent structure where the hydrogens, could even be angled further down because those 2 lone pairs are pushing down on those bonds. So that's the actual shape or molecular geometry of water.